Okay, I'm going to try to finish off this chapter, but also know that I will screw up the final questions. There's some pretty difficult ones here and there, usually theoretical. So again, this is the same technique over and over again. You obviously can't find when that is above 16, so you have to bring the 16 over, and you get x squared minus 6x minus 7. And you have to figure out when that is bigger or equal to 0. You're essentially creating this as your new x-axis and finding the intercepts. It's clear from this that the two numbers here are minus 7 and x plus 1. We'll create that, which means you have to figure out for, this is obviously a parabola, so is this, rather. You have to figure out it's upward facing, it is. It goes through minus 1 and plus 7, which means it's going like that. Well, since the 16 has become 0, we can see that it's above the x-axis, to the left of minus 1 and to the above of plus 7. So you say, for this to be true, x must be smaller or equal to minus 1, or x must be bigger or equal to plus 7. I'm not going to put it in the full notation, but that's what you'd say. And they're all like that. And there we go. Next one, I'll try to steam through the easy ones. This is already set for you. You just have to figure out how you can factor it because it's a cubic. But you immediately see that x can be factored out, and you get x cubed minus 8. And you just set this to equal 0 to figure out when it's going to be above or below 0. So x cubed minus 8 is x cubed equals to 8. So when is that equal to 0, rather? When x cubed is equal to 8, so you're only dealing with 2. You're not dealing with minus 2, because minus 2 cubed makes minus 8. So for cubes, it's not like squares. You only have the one answer. So that means this graph passes through the points 0, 0, and 8, 0. It's the only time it will equal 0. Now you have to know what cubic looks like. Well, this part here I happen to know means it'll slip and slide through that spot. That's what the cube part means. Well, I'll make sure on the thing, but cubics generally are like this when they're positive. This one is. So I know it's going to go through 0, 0. It's going to come up to 8, and because it's got to end up in this quadrant, I know it has to slip and slide through there. And I know it doesn't slip and slide through 0, 0 because there's only 1 here. If it was squared, it would bounce off 0, 0. If it was cubed, it would slip and slide through 0, 0. Because there's only one x, it goes straight through 0, 0 and slip and slides through 8. Now at 8, it's 0, 0, but 8 is 0, but everything to the right of that, it's above 0. And since they're looking for everything that is below 0 here, they're looking between 0 and 8. So it's between 0 and 8, and not including 0 or 8, because they're looking for below, not equals. That comes from your knowledge of cubics. Now, if you didn't have knowledge of cubics, you'd plug in 1 to the left into the equation to figure out is it positive or is it negative. Then you'd put 1 to the right of the 0 to see if it's positive or negative. Then you'd put 1 to the right of the 8 to see if the graph comes out positive or negative. And then you know if it's below 0 or not. That's how you do it if you don't know how the graph's going to turn out. So this one here is cubic, and they want to know when it's below 6, which is impossible. So what you're going to do is instead subtract 6 from both sides and end up with this. Well, for you to do this, you know it's a cubic, but you hopefully are able to factor it. So you have to figure out at least one factor. So the numbers we're dealing with are 1, 4, 1, and minus 6. And you just start with your 1. So 1 will lead to this. 6, 6. Right away you can see that 1 is indeed a factor. So you get x minus 1. And if you look at this, it's x squared plus 5x plus 6, which means it's x plus 2 and x plus 3. Now, on the number line, if you were to do it with number line, that one's gone, you would realize, okay, it's going to pass through several points here. It's going to pass through minus 3. It's going to pass through minus 2. And it's going to pass through 1. Now, if you didn't know how a cubic behaves, because you know that this is a positive leading coefficient, I already know it's going to do this, right? But if you didn't know, I would take minus 4, and we're looking for everything that's below 0. I know it says below 6, but remember we moved the 6 over. So everything below equals 6. So if I take a minus 4 over here, I get a minus, minus, and minus. And I know that would come out as minus. So that tells me the graph is going through. Right away, you should know it's going to be positive. But let's say you took a minus, and that's a minus 2, by the way. Let's say you put minus 2.5 in here. You get minus, minus, positive. So that tells you everything between these points is going to be positive. And it also, you know it's between those points because you know it's crossing the x-axis each time. And then when I take point between here, the easiest one is 0. I can see that it's minus, positive, positive, which will mean everything between here is negative. So that's another way to do it. So that means when x is smaller or equal to minus 3, it's below 0. And when when x is between minus 2 and equal to that, at positive 1, those are when the graph is negative. In other words, when it's below 0. Always keep in mind that once you've adjusted the number, you're no longer looking for below 6. You've essentially lowered the graph down to the x-axis. That's what happens when you subtract 6 on the left side. You've lowered the entire graph down to the x-axis so that it's solvable. It's not solvable otherwise. And that should take you back to your transformations, where whenever we had a number at the end of a graph, it always lowered it. If it was plus, it raised it by 6. And that's what we're doing. We're bringing the graph down to the x-axis so that we can solve it, using our factoring techniques. Really, it's just about how do you solve a complex problem using your known techniques. So this is a quadratic. And obviously it's already set, so you have to figure out, are there factors? Now, be aware we're missing a cubed, right? We're missing x cubed. So that the x cubed gets a 0. The x squared gets a minus 5, and we're missing an x. So the x gets a 0, and then we have the number 4. And that's actually what this equation says, but you never bother writing down the zeros. So we're going to work with 1 first. Nope, almost. But that last part makes 8. So we're going to try minus 1. Makes sense if 1 is pretty close. Yeah, it worked. So we know that x plus 1 is one of the factors because minus 1 was a root. Okay, now we just need to solve this next one. We're left with a cubic. Okay, and you should always see if 1 can work twice. So you're left with x cubed minus 1x squared minus 4x plus 4. And you're still doing the same thing. So we're left with a cubic here and a squared here. So the numbers in front there are 1, minus 1, minus 4, 4. Now, I didn't have to rewrite this. I could have just proceeded with synthetic division for this one. But it's still good to see. Now, notice a lot of numbers are the same. So I'm going to try minus 1 again. Nope. I'm going to try positive 1. Well, positive 1 won't work because we already tried it once. It didn't work. So I'm going to try 2. Oh, 2 worked. So that means the next factor is x minus 2. And remember your factor theorem. When the remainder is 0, it means it's a factor. So I'm left with x squared plus x minus 2. And I can see that the factors here are x plus 2 and x minus 1. So it's the opposite of those. And I thought I did minus 1 and couldn't figure it out. So I guess I must have made I must have made an error. So I'm just making sure. Anyway, assuming I didn't make an error, we're looking for when this graph is above 0. All right, we know it's going to go through minus 2, minus 1, 1, and 2. And I happen to know that a positive leading coefficient means it has to behave like that, which means it's above the 0 to the left of this minus 2. It's above the 0 between minus 1 and 1, and it's above the 0 over here. So I'd say it's above 0 when x is smaller than minus 2, when minus 1 is between, when x is between minus 1 and 1, and when x is above 2, assuming I factored it correctly. Okay, this one is a cubic, but it's got a lot of the stuff on the other side. When I bring down this 2 cubed over here, it becomes 1 cubed. When I bring this plus x squared over here, it becomes minus 2x squared. When I bring this x over here, it becomes minus 3x, and there's no number. So I'm left with 3x cubed minus 2x squared minus, 1x cubed minus 2x squared minus 3x. When is that smaller or equal to 0? Because I've moved everything to the other side. I notice right away that I can factor out an x. I'm left with x squared minus 2x minus 3, which means it goes through 0, 0. And right away I can see that this can factor out to x minus 3, x plus 1 are the only factors, and don't forget that x. And since this was a cubic, yeah, it's a cubic, and it has a positive leading coefficient that I could see when it was 1x cubed. It is going to behave like this. It's going to go up, down, and up. The 3 points it goes through are minus 1, 0, 0, and 3. Boom, boom, boom. When is that below or equal to 0? To the left of minus 1, between 0 and 3, and that's it. So that means it's below 0 when x is smaller or equal to minus 1, because they have an equal sign here. So smaller equals a minus 1. And when it's between 0, when x is between or equal to 0 and 3, which is the far right factor over here, 3. There you go. That's when this graph is below 0. And you had to move it. It's essentially saying, the original question is saying, when is this graph below or equal to this graph? And when you actually draw the two graphs in Desmos, you'll see the information that we got. The graphs will, this left graph will indeed be below this right graph at those points in the same domains we identified. That's the whole point, is we're trying to find a simplistic method to answer a complicated question. When this goes over here, we get 2. When this goes over here, we subtract 2x, so we get minus 5x. And when this goes over here, we get minus 2. So we're left with 2x cubed minus x squared minus 5x minus 2, and when is that bigger than 0? So you got to do the same thing we've done over and over again. Oh, didn't I just do this one? I think I just did this one. Oh, no, I didn't. Doesn't really matter. Yeah, I did. I just did that one. Sorry. Okay, moving on. Even if I didn't, it's the same technique. There's nothing complicated. For the following per function, determine when f of x is below g of x. So f of x is blue, and g of x is red. So what you have to do here is essentially take a vertical line test. I'm just going to make the graph a bit bigger. You're taking a vertical line test, and we're going to make it green, and you're saying, okay, where's the red compared to the blue in that spot? It's below it, right? But I want to see where blue is below g of x, so it's not in that spot. Right here, where it crosses, it's equal. So it's not below g of x, it's equal to it. But everything here, it's clear the blue line is below the red graph. Then here, it meets again, and red goes down below blue, which is not what I'm looking for. But from this point on, the blue is definitely below the red, which is what I'm looking for. So I'm looking for in between here and everything past this point. So in between here, if I go down to where they meet, it's minus 1. If I go down where they meet here, it's 1. If I go down to where they meet here, it's 2. So that means the blue line is below the red line between minus 1 and 1. And the blue line is below the red line when x is bigger than 2. And we don't do equals because they're looking for only smaller than. And those are how you explain where that graph is below the other graph. this actually does have some uses in science. A lot of students say, well, why am I learning this? Even in business, optimization curves about pricing an object, you want to see how much money a company will make depending on the price. It's why you see crazy price adjustments in some products, because they can make more. Even if they only sell less of them, they can make more money. So they want to know how you would solve this. So that just means you're taking the 10 and moving over here, and the 10s disappear. So this is the equation you're using to solve it, which is what they want to know. Explain how the graph of the corresponding function can be used to solve the original one. Well, the original one, there was a graph like this, and it's a cubic, so it's like this. And you want to see on that graph where it's above 10, the y of 10. But you can't solve that. So essentially, we're lowering the whole thing, the whole graph down by 10, so that this new y of 10 becomes the x-axis. This new equation that we're solving, when we subtract 10 from both sides, will tell us where it intercepts with the x-axis, which is the same as the intersection points up here, where it would have intersected y is 10. And then they ask us to solve it. So that means we're dealing with just this equation here. And when is this equation bigger than 0? Well, you're dealing with a cubic, and we're missing a number here. So the numbers in front are 1, 11, 18, and 0. So using, I can almost automatically see, we're actually start with 1. So use synthetic division. And I can see right away it's not going to work. And I'll try -1 just for the sake of it. Not going to work. So I'm going to jump straight to -2. Which works. So that means x plus 2 is a factor, and it means my remaining quadratic equation is x squared plus 9. And it's clear that that can't be solved. If I set this part equal to 0, I get x squared is equal to -9, which doesn't have a solution, which means this part of the graph is either well below or well above or well below the x-axis and never crosses. So it's only here that it crosses the x-axis. So instead of looking for above 10, we have to figure out what this graph does. Okay, well, I know it's a quadratic, and I know it only passes through this part. So it does this, and it goes through -2. And then it wiggles up here somewhere, actually probably down here it wiggles. And that means after it goes through -2, it just keeps going up. So if we're looking for the spot that's above 10, or when we adjust it above 0, it's everything to the right of -2. So when x is above -2, the graph is above 0. And when in doubt, you can put this original graph in and see if where it's above 10. So x cubed plus 11, 18, and 10. And then we're going to put the next line as y is equal to 10. I'm going to see where this graph, if it is indeed above 10. Oh, so I made a factoring mistake. So there's indeed is the -2, but I can see that it dipped down here. So I have to go back and see where I made a mistake. So when I bring the -10 over here, this is indeed the correct thing. And we'll go back and we'll test it out. Oh, make sure I got the right one actually before I do all that. Plus 11x squared. Plus 10, when is it above 10? Okay, let's try this again. So here's my new factor. The numbers I'm working with are 1, 11. It's good to graph just to see if you make mistakes like that. And I claim that -2 was a factor. Oh yes, there's a 0 here, the missing number. So -2 is a number, but I believe, what am I doing wrong here? When is it above 10? So when is the graph above 0? I still got the right factors. Oh, I'm an idiot. My bad. So that was not left over. That was definitely x plus 2 is a factor, but what was not left over was, it was not left over x squared plus 9. What actually was left over was x squared plus 9x, because this 9 is under the x squared. So that's my mistake, which means if I factor out x, I get x plus 9, which means one of the other factors is minus 9. That means this graph goes through minus 9, as we saw, comes back down at minus 2, and then goes back up at 0, which means it's going to be above 0 between minus 9 and 2 and anything after 0. And that is why this graph, we can see the negative is to the left here. Everything above is between these 2 points here and here. And that goes down below, and then everything above is after that. So that was my factoring error. But it's good that I pulled up the graph and caught it, because after all, that's what practice is. It's making mistakes and catching their mistakes. If anything, many successful people say they've learned far more than from their mistakes. Never consider a mistake or a failure. It's a learning. Okay, this is all theoretical, double root, oof, and I give them an answer. And I mean, I might as well do one of these to show that it's doable, but I really hate it. So they're telling us it's a quartic function, so x to the 4. They're telling us when f of x is above 0 is between this and that. Okay, so that's quite a bit of information. So between minus 2 and 1, this whole thing's above 0. Now just be careful, because it could do this. You just don't know. So we know the graph is like that, at least. F of x is below 0 when x is minus 2. So below or equal, so it's going to go down. Or when x is above 1. Oh. So they're telling me that even though it's above 0, or when x is below 1, okay, yeah, so it's going to go down. And it has a double root when x is 3. When x is 3. So that means this is a negative quartic function, because if it has a double root at 3, it means it's bouncing back. Since it ends here and begins here, this has a negative in front of it. They also tell us that minus 1 is equal to 9 to 6. Now you have a lot of information. You can write out your quartic function. You can write out its roots like that. And they told us it's got a double root at 3, so you can square it. Now you've accounted for all your factors, but there's always a number in front. Fortunately, they give us an answer. They said when y is 96, so this would be y is equal to, or f of x is equal to. They told us when f of minus 1, the result is 96. So that means 96 is equal to this whenever x is minus 1. So this becomes 1. This becomes minus 2. This becomes minus 4. Minus 4 times minus 2 is minus 8, or plus 8, and times 1 is 8. Now I've got to redo that again, because according to me, there should be a negative coefficient. So I'm going to go through. That's correct. The graph is below 0 and it's to the left of x, or above 1 and has a double root, so it bounces back. So I'm just going to make sure I interpreted what they're telling me. The graph is above 0 between 2 and 1. It's below 0 to the left of minus 2. It's, or above 1. And has a double root at 3. So it's going to bounce back. Okay. Just making sure x minus 3 squared. Ah, I forgot to square it. That's the problem. There we go. So I'm going to go back. And when it's minus 1 here, I get a 1. When it's minus 1 here, I get minus 2. When it's minus 1 here, it's 4, but it gets minus 4 squared. So it's positive 16. So I get minus 32. A times minus 32 is equal to 96. And I'm just going to make sure I got that right again. Minus 1 is minus 4 squared. 16. Minus 1 here is minus 2. So it becomes minus 2, and 16 times minus 2 is minus 32. And then minus 1 here becomes 1, so it's insignificant. So that means A is equal to 96 divided by minus 32, which makes sense. And I can see that that is equal to minus 3. So that means there's a minus 3 here. Now, if they wanted the full expression, you would then expand it all and multiply it all by minus 3. And then you'd have the full standard equation. So I guess that was worth doing. I don't know. The viscosity of oil used in cars is related to temperature. So that means as temperature goes up, the viscosity goes up. Or actually, with the negative, as temperature goes up, viscosity goes down. Where each unit of T is equivalent to 50 degrees of Celsius. So for each 50 degrees, when 1 T goes up, it represents 52 degrees. When 1 degree of temperature represents 50 degrees. Determine graph function on your graphing calculator. Well, thank you very much. But let's figure out also what a negative T graph will look like before we ever go to the graphing calculator. Okay. Since it's a negative T, it's going to start in this quadrant. It's going to go down, possibly cross 3 times, be like that. Since Y represents viscosity, viscosity will go down as temperature goes up. It'll deviate a little here in this range, but then it'll continue going down. So as oil increases by temperature of 50 degrees, the viscosity goes down. Remember, each unit on the x-axis will represent 50 degrees. Graph this in the graphing calculator to determine the temperature range for which the viscosity is above the graph to 2 decimal places. So the reason I want you to graph it is it can't be factored. So we're going to go, we'll do f of t is equal to minus t cubed to the power 3 minus 6t squared Gotta get rid of that plus 12t plus 50. So that shows you at 0 the temperature is 50 degrees because you've got a y intercept at 50. So it's 0 time, and really when they're talking about time, they're only care about when the time is bigger or equal to 0, because we don't really care about back in time. So they would really only care about that, but you would keep the whole graph for now. So they want to know when the graph is above 0, so clearly the graph is above 0 to the left of that. It dips down below 0 here, and so it hits a very low viscosity here. It starts coming back at a certain temperature. And really, it would only be concerned, so when the temperature first goes up, the viscosity goes up, and then as the temperature increases, viscosity starts to dive. And at this point, I don't think the graph would be relevant because viscosity below 0 wouldn't be an issue. But let's look at their question. Determine the temperature range for which V is above 0 to 2 decimal places. Okay. To the left of an x is to the left smaller than 2.42, and when x is between, when x is smaller than negative 6.78, negative 6.68 because I wanted 2 decimals, and when x is between negative 2.42 and 3.10 because they want you to round up to 2 decimals. The 5 makes the 910, which makes the whole thing 3.1. So that's the only time viscosity is above 0. Determine the temperature ranges for which the viscosity is between 15 and 20. So for this, you just say, okay, well, I'm going to make my y 20 and my y 15. And between those temperatures of x values, that's when my viscosity, so there's the 20 and there's the 15. So between negative 1.791 times 50 and negative 1.58 times 50. Oh, by the way, you had to take those original ones I gave and multiply them by 50 as well. The viscosity is between 15 and 20. And then over here, the viscosity is between 15 and 20, between 2.676 times 50 and 2.759791 times 50. Those are the 2 times this graph falls between, and actually 3 times, yeah, over here as well. Those are the 3 times the graph falls between. Now, obviously in real life, you wouldn't care about negative time, or negative temperatures rather, because there's no such thing. So you'd really only care about all the positive, everything to the right of 0 on the x-axis. And the book might even say that. But just looking at the graph, there's clearly 3 zones. This one, and this one, when the viscosity falls between 15 and 20. And you can only determine that with a graphing calculator, unless they gave you a lot more information. All right, going onwards. A rock is tossed from a platform. So usually, if it's tossed, they usually have some thing where it goes up for the first little bit. Let's look at when the information we have right now. It's a negative downwards parabola. So it's going to be like this. When time is 0, the height is 14. So already we know on the y-axis we're talking about at 0, 14. Well, how high is the rock off the ground when it is thrown? Well, I just answered that. At time 0, it's 14 meters, I guess. Yeah, meters. How long is the rock in the air? So for that, you need to find, so it's probably going to go like that. For that, you need to find, and you wouldn't care about this part. Since time only starts at 0, you don't care from this to when it hits the ground. But to really have a good idea of when it hits the ground, we have to factor. When does it hit the ground? When height is 0. So that means we have to factor this, and we pretty much are going to use traditional methods, I think, because a number can't be factored out of each of them. If you want to make it a little easier on yourself, you can put minus 1 out of it, and you're left with 5t squared minus 12t minus 14. So you're looking for when a number multiplies out to minus 70 and adds up to minus 12. So you're going to look at a plus and a minus number. They're going to be fairly, well, they don't have to be close together. Let's look at all the factors of 70 and 1, 35 and 2. This can be divided by 5, and this can be multiplied by 5, and you get 7 and 10. And I didn't really have to do that. So far, none of these add up or divide by this. So we should look at a number that's divided by 5. So it would be 5 and 14. And that's close, but no cigar. 5 and 14. That adds up to 9. That adds up to 3, or subtracts to 3, 33. So because it's 9 and this is 3, I'm looking for something maybe 15 goes into it. Yeah, 15 goes 3 times. There it is. No, does it go 3 times? No, it goes 4 times. So that would be minus 11. Interesting. Do I have to take a quadratic, or am I just spazzing out? Yeah, pardon me if that offends anyone. So I'm going to take minus 5, 12, and 14. I'm going to go this. I'm going to take minus 5, 12, and 14. And sure enough, I had to use the quadratic equation because it was not factorable. And you should do the quadratic equation or practice it on your own, but I'm not going to bother because that's pretty basic stuff. And I determined that one of the spots is minus 0.85 seconds, but I don't really care about that. The other spot, and how much do they want? Well, we'll just round up to 2 decimals. The other spot is 3.26 seconds it hits the ground. So how long is it in the air? From 0 to 3.26 seconds. So that's how long it's in the air. What time's the height of the rock greater than 17? Well, that's going to be factorable. So when is this rock greater than 17? So it's clear it starts at 14, and it's clear it goes up. You could do this several ways. You could actually find the vertex and then find the number of times it is away from the time it is away from 0 and the time it is away from this point. So that'll be double the time that it hits this area. However, they're looking for 17. You could also find out, there's several ways to do it. But anyway, let's do it the way they want. They want to know when it's greater than this. So when is this equation greater than 17? Well, we've got to bring the 17 over. And we get minus 5t squared minus 3. Right? That's what we get. And when is that bigger than 0? Now this one's probably factorable because the x-axis weren't. So now we're looking for, if you factor out a minus 1 again, you'll make your life easier. You're looking at 5t squared minus 12 plus 3. And you might say, well, doesn't that affect the roots? No, because I've changed all the signs, it won't affect the roots. So I'm looking for something that multiplies out to 15, but adds up to negative 12. So we're looking for two negative numbers. And it is, geez, still couldn't do it. Do I have to do it again? And when is this bigger than 0? Yeah, 15 minus 12, so it's not 5 and 3. It's not 15 and 1, and there's no real other factors. So again, you need to use the quadratic. So I got 5 minus 12 and 3. And I determine it happens between these two time ranges. On the way up, at 0.28 seconds, it's above 17, and on the way down at 2.11 seconds, or 2.12, it's, so all during that time range, it's above 17. How long is a rock above a height of 17 is the subtraction of these two. Because at 0.28 it started entering the zone, and 2.1 it entered the zone, so 2.12 minus 0.28, or just 0.28, and I have to borrow it here, I get 4, I have to borrow it here, I get 8, and I get 1. So 1.84 seconds it was above 17. You could always graph it, make sure. And based on how many mistakes I make, it's probably not a bad idea. No, 14, wasn't it? Okay. And then you're curious about when it's above 17, right? And so sure enough, you can see that indeed the rock starts at 0.14. It indeed hits the ground at 3.259 seconds. They might have asked us to solve them. They should have asked us to solve the maximum height of the rock too, but they know that that's not relevant to what they're examining. And you can see it started entering 17 here and ended 17 there. So our quadratic equation was correct, and none of these were clean factors. But essentially, and I want to show you what happens by lowering the graph. We took this whole graph to figure out where it hit 17. We brought the whole graph down, and we will get the same x-intercepts as we would have up here. See, 0.238, 2.7. By lowering the whole graph by 17, we're able to find out where it has its x-intercepts, and it will be the same as the 17 intercept up here on the original graph. That's why we're doing it. Okay, I'm going to go on. Now they love these ones. The secret to these ones is realizing that if I have a corner x, I'm cutting out this little corner here, and it's a box, so both sides will be the same. And if I call them x and x and x, this part here will be the top of the box, because these little corners allow you to fold up the box on these dotted lines. But what's also interesting is there's a maximum x can have. There's a maximum x can have. And you see the whole length of this little box is the original length, 30, minus 2x. Well, if this minus 2x gets above 30, we have a negative dimension, and you can't have that, which means x here cannot go above 15. It can't even be 15, because 30 minus 30 is 0. You can't have a 0 dimension. So right away you know that x must be smaller than 15, and that's an important thing to notice. And you always use your shortest side because that's the side that gets swallowed up the fastest by 2x. This other side is also, of this box here, is also 50 minus 2x, because there's an x here and an x here. Okay, write a polynomial function to express the volume. Okay, to do that, oh, you might say, well, they didn't give us the height. Yeah, well, the height of the box is x, because when you cut out x here and you fold the flap up, this here becomes the height of the box. So that means the box's dimensions are 30 minus 2x by 50 minus 2x times x is equal to the volume based on x. For me to solve this, I can't keep the numbers like that. I have to expand it. Determine the range of the sides and lengths that are possible for each square. Yeah, so you can't have above 15. And remove that result in a volume greater than 4,000. Determine the length, range of sides of the lengths that are possible for each square. So that means when will volume be greater than 4,000? So they're going to ask us to solve that. But let's first write out this equation. 30 times 50, and you'll find your numbers end up in the wrong side. It's 1,500. 30 times minus 2x times 50 is minus 60x minus 100x, which is minus 160x. Then minus 2x times minus 2x is plus 2x squared. Now you have to multiply everything by x. So you get x squared here, and x cubed here. Put it in the right order. You get 2x cubed minus 160x squared plus 1,500x, and no number is equal to the volume based on x. Okay, so that's what you get. Good. So that's the quartic. Sorry, that's the cubic expression for volume. All volumes will be a cubic expression. That's why you see meters cubed. All areas, surface areas, will be represented by a quadratic equation, which is why you see meters squared as the result. And all single line equations, of course, will be represented by just x, or 1 to the power of 1, which is why all line equations are simply in meters to the 1. Or meters, you never say to the 1, right? And then as you get into the 4, you're entering into science where things are moving through time. Or moving, just moving. Because you can count motion as a fourth dimension. You can count time as a fifth dimension. Although, since motion is related to time, the fourth would be time. And you will indeed get into graphing vectors in an x, y, and z dimension. 3 dimensions. Surprisingly useful and follows a lot of the same rules as basic math. Oh, I accidentally deleted all my equation. There we go. Now, fortunately, they didn't want us to try to factor the original equation, and that's probably because it does not factor. However, we know that this is a cubic, and it could possibly do this. So obviously, there's going to be a range here that's above 4,000, and it could be 2 ranges. It could do this. And this range could be above 4,000 in this range. So they want to tell us, they want us to find out what are my values for x. And be very careful, because x, that's above 4,000, because x won't tell you the dimensions. 50 minus 2x and 30 minus 2x will tell you the dimensions. Determine the range side lengths that are possible. Okay? So let's just remember that x must always be smaller than 15. So we also have a domain limitation between 0 and 15. So we know we're only concerned with this part of the graph. Because negative dimensions, negative x, don't matter. So let's solve this. We've got 2x squared. We've got this. Minus 4,000 is it bigger than 0? Right, so that's what we're working on. We immediately see that we can factor out a 2 from everything. It'll make your life easier. So you're left with x cubed minus 80x squared plus 750 minus 2,000. And is all that bigger than 0? By the way, this also goes through origin. This original graph, when it was just equal to the volume, because I could factor an x out of everything, and I'm left with a quadratic. So I know that it's going to go through 0, 0. the original graph. And it's probably possible to factor it more. Because once I factor out the 0, I'm left with a quadratic equation. So it could have been very solvable. But let's just move on. So we're working with this. There's a good chance they're going to give us one dimension. And the numbers we're working on with are 1, minus 80, 750, and minus 2000. So normally what I would suggest is grab a calculator and go through one, but I'm going to just try a couple dimensions here. 1, 1. I know that's not going to work. So what's a couple factors? Let's go with, let's try 10. Oh, and by the way, I also know it's going to be minus because, no, 10 is what I'm going to start with because I want a positive mention. Close. Let's try 5. Five times that is half of this. So get a minus 375, which produces 375, and times 5 times that does not produce that. Does not produce 2000. So what I'm going to do is I'm going to pretend I have it in a calculator. I'm going to turn off this graph. And I'm going to call it volume based on x. And it's going to be a 2 and x cubed, just to speed up the process, minus 80x squared. So you'd punch this into a formula, into your calculator, and they can do that now. All these calculators can. So minus 80x squared plus 750x minus 2000. And then I'm just going to do this, v of 1, v of 2, v of 3, v of 4, v of 5, 6, 7, 8, 9, 10. Well, maybe I don't have it properly. V of 11, v of 12, 13. I think I had to start with get into the negative zones just to get a quadratic formula out of it. No. Did I get it right? Did I expand? Let's check my expansion. So 50 minus 2x. Oh, not 2x squared. Stupid. It's 4x squared. I think I even said that. 4x cubed. How many mistakes am I going to make? And when I take the 2 out, it's leaving 2. So this whole thing has actually got a 2 in it. Dumb mistake. Which means the factors are not these. This is 2. Which affects everything. And I'm going to just continue back here and just, actually, you know what? Let's do it old-fashioned style. Go back to that 5. 2, 10, minus 70, minus 350, 400, there it is, 2000, there it is, right there. So I got x plus 5 is one of the values, or x minus 5. So one of the roots are that. And we'll have 2x squared. I could have factored out another 2, stupid. Minus 70, plus 400. Let's factor out another 2. I'm left with x squared minus 35 plus 200. This whole thing in front now should be a 4 plus 200. There we go. Now I'm left with this, which probably has a negative and a positive root. Actually, it has 2 negative roots. So that means there's 2 more negatives. There's 2 more dimensions. Now, if it's above 15, though, it doesn't exist. So I'm looking for a number that multiplies up to 200 and adds up to minus 35. So 20 and, oh, they're both going to be negative. 20 and 10. That looks close. Make sure I got my, should make sure I got my factors right. Let's just continue. 35, 20, and 10 was very close. So we'd be looking for, let's let the quadratic equation solve it. 1 minus 35 and 200. Assuming I did all that right. Yeah, so I get odd ones after this. The two roots left over are this. This one can't be a possible dimension because it's above 15. This one can. So rounding up, my possible dimensions for x are 5 and 7.2. Assuming I haven't made any errors, and there's a good chance I have. That means that my length's 30 minus 2x is 30 minus 10, so 20. And 50, actually that would be the 50 here. And 30 minus 10, 20. And the height would be 5. So this is one possible dimension that's above 4,000. So that x would have to be bigger than 5. Oh, and then you'd have to look at your, so the other one was 14. So which means that the graph, which was a positive quartic, goes through 5, comes down through 7, and then comes back up through 17. So these are the only possible dimensions where it's above the graph. So between 5, when x is between 5 and 7.2. So what you would do is figure out the two possible dimensions. So when the box side, they just say side lengths? So they just want side lengths. So that would mean 30 minus 2x. So when the side length is between 20, is smaller than the side length. And between 2 times that is 14.4, and 30 minus that is 15.5. So when the side length is between 20 and 15.5. Let's see if I screwed that up or not. 4x cubed minus 160x squared. Okay. So this is the one that's been adjusted. We can see it goes up. We can see it also goes up when the x is way over there, but we're not concerned with that. And we can see the x values are indeed between what we thought they were. If you take the original graph, that's it. You will discover when you set the y to equal 4,000, and you go up there, and to do that, to make it easier, just set your y-axis between that and 4,000, and you discover the same things between 5 and 7.92, and then over here. You have to turn off the first graph to not get confused. And then over here, which is a dimension that can't exist because x is too big. So that's the same thing on the original graph, and then we lower the whole graph by 4,000 to get it on the x-axis and figure out the same thing. I made it a lot more complicated than it had to be. Without a calculator, explain why there's no inequality, why this has no solution. Oof. I think just because this boosts it so far above the graph, and it's a possible W. Without a calculator, explain why this has a solution. Now, we can try the second one. I think the first one is just logic. I'll show you the logic of it. Now, other than 0, so let's take 0. When this is 0, it's clear the remainder is 80, and 80 is not below 0. When this is 1, it's clear it's 2 plus 1 plus 15. They're all pluses, so it's going to be 80. That means I'm only concerned about minus 1. When this is minus 1, I get still positive 2, and still positive 1, and still positive 15 because it's squared with a 4 and 14. So no matter what numbers I take between 0 and 2 and 0 and minus 2, I get positive results, and there's always that 80. It can never be below 0. 80 can never go below 0. And it's also obvious as I take bigger values of x, this number takes well over everything compared to these. But regardless, because these are even exponents, and they're all being added, no matter what negative number I put in there, the whole thing becomes positive and can never be below 0. So that's the logic. Without a calculator explaining this, has a solution somewhere. Okay, let's start by, once this 30 comes over, I'm no longer adding 20 to the whole thing. It becomes minus 10. Once this 11x squared comes over here to minus 11x squared, I get minus 4x to the 12 minus 7x cubed to the 6 plus 9x squared minus the 11x squared, so it becomes minus 2x squared minus 10, smaller than 0. It's quite clear when I take x as 0, I'm left with minus 10. And minus 10 can indeed be smaller than 0, because remember we moved everything else to the side, which makes that a 0. It's very clear that when x is 0, I get minus 10. Even when x is 1, I get minus 4, minus 7, minus 2, minus 10. All that's well below 0. And even when I'm taking a positive or a minus number, they're getting cubed and squared. And all these minuses are multiplying it. If anything, I would say this graph is never above 0. It's always below 0. In other words, this graph is always below this. Makes sense because this is an upward-facing parabola, and this is a downward-facing W. And yeah, when it's 0, it has 20. But when this one's 0, it is 30. And 20 is definitely smaller than 30. So this graph over here is clearly going to be below this graph. You're going to have a parabola like this. You're going to have a downward-facing W, and the closest I get is, let's say, 0. But that's at 30, and that's at 20. So that's all pretty much logic by plugging in numbers and seeing that no possible. Okay, they're saying the explanation they gave us is incorrect. Let's see if we can just spot where it's incorrect. So they're saying when you divide this by x plus 1, you can cancel out this. But the problem with that is, while that's mathematically correct, those are no longer the same graphs. This is a parabola, x squared, minus x minus 2. And this is also a parabola, x squared plus 5x plus 6. And I believe what the problem how this doesn't work out is this minus should actually be in front, and it becomes x minus 6. And that's what gets all snafu'd. And it looks for values x above 4, but you actually have to expand it because you're looking at one graph versus another. When you cancel out like that, algebraically, it's a trick. But that x plus 1 is still in the graph somewhere, so you can't just compare these two lines and say, oh, they're just lines. When is this line compared? When is this line here bigger than this line here? Well, of course, a line's going to be bigger than another line, but that's not what's being compared. What's being compared is a parabola. When you look at this parabola, it is an upward-facing one, right? It's an upward-facing one, and it goes between minus 1 and 2, which means that minus 1.5 will be the vertex. And you'd figure it out. Minus 1.5 is 0.5 times minus 3.5. So it's at minus 1.5, negative 2 point something. This other one is a parabola, but this becomes minus x squared here. It's downward facing. And if you factor out that correctly, you get minus 1 up front, x plus 6, and x minus 6, which means it goes through 1, it goes through minus 1, and 6. Am I doing that right? And it's downward facing. Well, at minus 1 and 6, the in-between point for those is something like 2.5. So there's going to be a vertex somewhere. So let's see. If I take minus out of it, I get x squared minus 5x minus 6. The vertex is going to be at x minus 2.5 squared. So 2.5, and if I plug 2.5 into it, I get 3.5 and roughly 8.5, which is about 24. So somewhere in there it's going up to 24. So this is not the correct solution. They do cross. So I'm going to show you the graphs. So we just do x plus 1, x minus 2. And I'm going to show you the other graph. Minus. Oh. And I'm going to zoom in. And there you go. So between those points, minus 1 and 4, the green graph is indeed above the red graph. Now you could solve that algebraically, but you'd have to expand it. So you'd have to expand it the way we expand it. You'd have to have the correct terms. It has to be minus x squared. And this would have to be a plus 6x, and this would have to be a plus 6. When you bring the things over, you get 2x squared plus 4x plus 4. You take a 2 out of both of them. You get x squared plus 2x plus 2. That's not clean solutions, but this one did come to clean solutions. So let me go back and expand them correctly. So the first one is definitely x squared minus x minus 2. And the other one is minus x squared plus 6x minus 1 plus 5x plus 6. When I bring the 6 over, I get 4. When I bring the 5 over, I get minus 6x. Okay. When I bring the x squared over, I get 2x squared. And when I take the 2 out, I get x squared minus 3x minus 4. Well, actually, it's even worse than that. Because plus 6 is minus 8. And it's left with minus 4. And it's clear that the factors of that are x minus 4 and x plus 1, which means this is a upward facing now, an upward facing parabola. And it'll be above 0. Where's it downward facing? When is it above 0? So when is this first graph above the second graph? So when is this red graph above? Oh yeah, so they're actually looking for these sides outside. The only time that's not true is between these points. So everywhere below x is minus 1, above x is 4. The graph is, the green graph is below the red graph. Or the red graph is above the green graph. You just have to know which one represents the graphs. But once we solve it, we do indeed come up with this, and we realize everything to the left of minus 1 is above 0, and everything to the right of 4 is above 0, which also answers that question. But you can't cancel out and create lines. That's algebraically it looks good, but it's not the right way to do it. Okay, moving onwards. There's only a couple left. When is this graph below 0? Huh. Oh, I don't know if I could solve that last one. We'll try 17, but it looks tough as well. Let's try to figure out the graphs. We'll start with this one. They want to know when this graph is below 0. So at the top, you get x plus 4, x minus 3, and at the bottom you get x plus 2, x plus 3. None of them cancel out. Is this graph below 0? Oh, hang on, let me just do that first. There we go. That's the first one. So you can see that none of them cancel out, but you can figure out asymptotes. So an asymptote down here is, it's a plus, right? Yeah. You can figure out the asymptotes here are at minus 3 and minus 2. And you also know a horizontal. These x squares are the same, so when y is equal to 1, these things will behave differently. So all you have to do is figure out, you have to make a box, and you have to figure out what happens to the left of minus 3. Is it above 0? Is it above the asymptote or below it? So at minus 4, this becomes, oh yeah, and are there any, where's across the x-axis? Across the x-axis here at minus 4 and at 3, because that's when this top part will be 0. So right away, I can tell you, at minus 4, there's an x-axis cross, right? So that since we know it hugs the asymptote either here or like that, I know that it has to go like that, which means between here, minus 4, and this asymptote, it's going to be below the graph. Now, going to the other side here, the other asymptote, or the other x-intercept, was at 3, which is way over here. Now, since I know that it's got to go up and hug, I know it's going to cross through 3 like that, which means everything between 3 and minus 2 is going to be below 0. And I just know this because I know it's got to hug the asymptotes. And since I found out on the left, one of the x-intercepts is to the left of one of the vertical asymptotes, that means the graph has to be below this y is equal to 1. So I know between minus 4 and minus 3, the graph goes below 0. Same with between 3 and minus 2. The graph goes below 0. The only question is, in the middle here, does the graph dip? So what's in the middle between minus 3 and minus 2? Minus 2.5. So here you're going to get minus 2.5 is going to come out positive. Here minus 2.5 is going to become out negative. Here minus 2.5 is going to become out negative, and minus 2.5 is going to become positive. This becomes negative up top, this becomes negative at the bottom. A negative divided by a negative is a positive, which means the rest of the graph here, and I already know it doesn't cross the x-intercept, so the rest of the graph is up here. This is the only spot between there that it can be below 0, and that's how you solve it. Let's see if it's true. So x squared plus x over 12, f of x is equal to, let's just use the factors. X plus 4, x plus 3. X minus 4, right? Was it x minus 4? Ah, made a small error. So, that x minus 4 here. So it's supposed to be x plus 4. Oh no, I figured it out right. I just did the x-intercepts up there. So it's x plus 4, x minus 3. And the other ones, factors, were x plus 2, x plus 3. So right away, I'm going to put my asymptotes in. So there's my two asymptotes. And I'm only going to show the graph when it's smaller than 0. So it even outlines it for me. The graph is below 0 between the -4, and it's below 0 between the 3 over here and -2, which is exactly what I said. If you just want to see the graph, though, here it is. I'll get rid of the, there we go, I'll get rid of the x-intercepts. And you can clearly see the graph is below to the right on -4 and -3. Now you cannot just say between -4 and -3. You could, but then you have to say, but x can't be -2 or -3. So you could say this, -4. You could say, I'm going to just get rid of a lot of that. You could say it's x is between -4 and 3, but then you'd have to say it, but x cannot be -2 and x cannot be -3, because you have to include, or +3, whatever was the other asymptote. There we go, -2, -3, because you cannot have the 0 at the bottom of the graph. I hope you've watched the other video, because that's a fast version of graphing. Let's look at this one. Factor the top, you get a difference of 2 squares, x plus 5, and x plus -5, which tells you immediately it goes through the x-axis at -5 and 5 on the 0. The bottom factors out to x plus 5, and x plus 1. Now, right away, I can say, okay, it doesn't cross the x-axis. There's a hole there. There's a hole. But I will have to remember that -5, 0 is sort of would normally be an x-intercept point. But as for what this graph looks like, you would draw here, and this time they want to know above 0. And you'd say, okay, it's going to go through 5, 0 for sure. If I look at x squared, x cubed, this power's smaller. Oh, look, I can't factor the bottom. It's x cubed. I have to factor out an x first. Let's go back and get the correct factors. So up top, I get x plus 5, x minus 5. At the bottom, after factoring out an x, I get x plus 2, x plus 5, x plus 6. That makes a difference. I can see that there's definitely going to be a cancel out here, but I want to remember that there's a hole that essentially would have normally gone through there. I also want to keep those factors for when I'm doing the test. Well, actually, no, it doesn't matter. So I'm going to cancel out. I'm going to create a hole there. So I no longer have an asymptote there, but I do have an asymptote when x is 0, and when x is -6. I also know between that point there's a hole, so it's probably going to cross through between -5 and here, -6. This is 0. So all I need to know, oh, is there a horizontal asymptote? Yeah, at the x-axis, because these powers are different. So all I need to know is what happens. I know also here it crosses through the x-axis, right? So I know there's either this, which is likely, or this, which is less likely. So I still need to know what happens between 5 and 0. What's a good number to take between 5 and 0? 1. Okay, let's look at these factors instead. I get minus here, 1 here, 1 here. So minus divided by a plus is a minus. So that means it goes through 5, 0, and it goes down. And then it crosses through 5, 0, and then it's going to hug the x-axis. So that's important to know. Which means after 5 and up, it's above 0. My guess is this is going to go through here. And because it doesn't cross any, well, no, there's an invisible thing, a hole there. So it might cross, and it might cross and do that. So we need to really find out what happens between 0 and -5. Let's take -1. Here this becomes minus, this becomes minus, and this becomes plus. So it ends up being minus divided by minus, which is plus. So over here, here is going to be a plus. Now I know it doesn't bounce back because that would be a square, which means it goes through. So that means between minus 5 and 0, the graph is positive. Just to make sure, you can take minus 5.5, which is close to this, and you get minus, minus, plus. Oh, hang on, let's try that again. Let's try it again. What happened if I take, let's make sure at minus 1 it's minus. I get minus, minus, and plus. Yeah, it becomes positive. Let's take minus 5.5. This becomes minus. This one becomes minus. This one becomes plus. So that's plus as well, which is weird. It means it does a weird bounce back, which means that whole area is above 0 except for 5. That doesn't make sense to me. And I don't have to include the x plus 5 because whether they come out minus or not, they will cancel each other out each time. So let me just make sure. At minus 1, this is a minus. Minus 1, this is a minus. And at minus 1, this is a plus. It wasn't x plus 6, though. That wasn't one of my factors down below. It was x plus 5. So x plus 5 and x plus 1. That's what's going on. So it is not minus 6 over here. It is minus 1. It was x plus 5, x minus 1. I wrote it down as x plus 6. The x plus 5 is canceled out. So that's what's going on. So that means this is not, I cannot take minus 1 as an option because that's the asymptote. To figure out what's going on, I know it doesn't cross the x-axis anymore. What's going on at minus 2? So minus 2, this becomes a minus, this becomes a minus, and this becomes a minus. So the whole thing graph is going to be below over here, which means in between minus 1 and 0 is what I'm concerned about. So I have to take minus 0.5. Minus 0.5 here becomes minus here, but it becomes positive here. So that means the whole graph here is going above. And yes, minus 5, 0 is a weird hole, but it's going to happen in a graph below the x-axis. So that means this whole area here between the asymptotes, the graph is above 0. Let's see if we got it right. And it's also above 0 to the right of 5. See if we got it right. So it's x squared minus 25 up top. We're going to use the original graph in case I factored wrong. And the other one is x cubed plus 6x squared plus 5x. Okay, so there's that point where it crosses. So all the values to the right of that. Oh, it crossed again, though. It crossed again. Why is that in there? Why is that showing me a dot? Oh, I guess I just clicked on it. Okay. To see if it crosses the asymptote horizontal, you just make y is equal to 0, and you'll see just one dot right there. You can also make the whole equation equal to 0, and it will tell you where it crosses. So I got that right, everything to the right. Then there's that stuff I'm talking about. When x is equal to minus 1 and when x is equal to 0, that stuff at the top is positive. Now, it looks like I did one thing wrong here. Oh, no, I didn't. So that's that little mysterious part between the two asymptotes that is positive. This left side, negative all the way. So got it right. The important thing was catching the mistake on the asymptote, and that's because I rushed it. But that's how you figure them out. You got to factor them, figuring out their asymptotes, figure out what the graph is doing on either side of the asymptotes and the x-intercepts, just like you would normally. Solve this algebraically. Oh, when is this graph above 0? Well, let's start with this growth graph. This graph is normally hugging and going up. And it's going to go through the spots 1, 2, and 0, 1. But when x is 0, this becomes 1, and this becomes minus 2. So the whole thing would flip. So you'd have to just say, when is this equation positive? Because you know the growth curve is always positive, so this is always positive. So you know this is always positive. When does this become negative? Well, when x is 2, it becomes 0. So we know that when x is 2, the whole graph becomes 0, which is equal to 0. And when x is minus 1, the whole graph becomes 0. And so that's also equal to 0. So we just need to figure out what happens between those points. So now all of a sudden, we have a graph where the growth curve is never 0. It's always positive. But we can see at minus 1, we're going to go through a thing. And we can see that through 2, we're going to go through a thing. We just have to say what happens with that graph in between those points. Because the growth graph is always a positive. So what's a point between minus 1 and 2? 0. So when it's 0, this is 1, and this is minus 2, which means the graph is going to be negative between those points. And every other time, when we're below minus 1, so minus 2, we get a minus, and minus 2, we get a minus. It makes a positive. And when we're above 2, it makes a, let's say, 3. This makes a positive, and this makes a positive, which makes a positive. So this whole graph dips down. I don't know, it won't look like this, but it'll only dip down between those 2 points. And it will be equal to those 2 points. So when is above 0 or equal to 0? When x is smaller or equal to minus 1, and when x is bigger or equal to 2. Now, solving algebraically is a little bit difficult. You'd have to sort of graph it, because you're left with x squared minus 2x plus 1x minus x minus 2 times a positive integer, very small on the left and very big on the right. So you'll be looking at, and this is a parabola, so it's doing this. So here, I mean, it's sort of going up. So what you're looking at is, and this is going to be consistent, so you can see this weird parabola that dips below the 0 and then just goes skyrocketing up. Solving it algebraically, I mean, I guess you have to say you have to do what I just did. You have to do a number line and say when is it above 0. But let's see what that looks like. X plus 1, x minus 2 times 2 to the x. Now let's see if I can predict it. I'm going to say because the 2 to the x graph is like this. Come on. And the other graph is like this. And if I just take a snapshot of that, I'm going to say when I add these, when I multiply these values, this number is pretty much the same. So it's going to kind of go like that. These numbers from this point on, it's all going to become negative. And it's multiplying pretty consistently. So it's going to do a weird bump down and then up. And then this part's just going to go shooting up. So it's going to be slightly arced like that. This part's going to be shooting up. And there's going to be, when it cuts through here, it's going to go down, but it's going to do this weird thing like that. Let's see. Well, the only part I screwed up was the left side, where it kind of goes up and then gets dominated by the growth curve, which I guess makes sense because the growth curve is going to be almost 0. So I didn't get this bump correctly, but I did get this shape right. Notice that's the only time it's below 0, and everything else to the left is above 0, and everything else to the right is above 0. So I got it right. I don't know if that counts as algebraically, though. And that's it. Sorry some of us were bumbling, but the process is accurate.